Exactly 1 month ago, I went viral on Twitter. My post is an engineering deep dive on how we made DeepSeek outperform Opus 4.7. And that is what we are going to discuss today. Just about a month ago, DeepSeek went ahead and launched their V4 family, DeepSeek V4 Pro and DeepSeek V4 Flash. And I started looking at that in a very different way. There were two groups of people on Twitter. When DeepSeek V4 Pro and Flash were launched, the general sentiment in the community was kind of not really an even split. There were a lot of people that I respect a lot who were saying this is a really intelligent model. So a lot of people that I respect in the community, they were saying things like, "This is a really intelligent model. The cognition level it has is amazing. It's probably like Opus tier model, and it is fast and it is quite stable." But at the same time, there were like probably 80% of the community, which I think were probably saying things like, "It is super slow. Tool calls do not work." Right? And this is the thing that I kind of want to focus on, right? Like, why were a lot of people saying that tool calls are not working? Like, what was so different for them in these guys, right? So I started looking at it, and we had shipped a DeepSeek V4 probably the same day or the next when it dropped in the community, and I had like a bunch of data on error stack in command code, and I saw something completely crazy. DeepSeek, being an open model, has a lot of tool calling issues, and I started looking into that. And I remember, like, it was Friday. My team was actually going off, and they were thinking, like, yeah, it's how open models are. But I was still looking into it, and I was like figuring out, like, maybe there is a fix here, right? I'm not gonna fine tune DeepSeek. I'm not gonna fix the pre-training, but maybe there is something I can do in the harness that can improve the performance and reliability and stability of the tool calls across the board. And I ended up discovering something that we have now been calling repairs, tool repairs, and we have this huge tool repair harness in command code that outperforms most every other coding agent harness in the market, especially for open models. And this is the reason why, right? So let's actually just go through this post so I can share what I discovered, right? So I've been thinking a lot about why are open models bad at tool calling. Now I'm almost sure like it's always a harness problem and not a model problem. Models are going to hallucinate. They're going to go make mistakes, and that's why the harness should be able to figure things out for it, sometimes deterministically, sometimes non-deterministically, right? This, however, is a deterministic fix, right? So the thing is, we are building command code, and I ended up looking at the tool input repair layer that we are building. This is like a review of that, right? And what I saw was that DeepSeek V4 Flash was consistently failing on our slash review skill that comes bundled with command code. And every shell command, the read file call was bouncing back, and there were like on average 56 failures per tool call for shell, for read file, for slash review, for DeepSeek V4 Flash. And I was like, this seems like a big pattern. The model should not be that bad, right? And I was at the very, brink of like, okay, maybe we should stop offering this model because it's not good enough and we can't really do anything about it. And the last thing I did about that was maybe I can run our internal benchmark and see how we can kind of like make a blog post on, we are probably removing DeepSeek from command code and it's not good. It's not doing tool calls at all. We tried a bunch of different ways, and I was trying to prove that, it's just a bad model and it's not working. Then I've been building something, and that thing is called taste. You all know that. Like, and if you want to go to our docs and take a look at our taste model, what that is, be my guest. Taste is a continuous learning layer, right? And I built it because I wanted my coding agent to learn from me. I have been writing code for 27 years. I've built so many things. If you go to my GitHub, you will see like I have like maybe 300 plus open source projects. 70 of them are probably really good, but everything else, I have like maybe more than 1100 repositories that are open source now, right? So I have a lot of thoughts and opinions about how software is made. And when I'm using coding agents, I want them to be learning my taste. They should be learning how I prefer things, right? So I built this taste model with my team. And the idea was that if you look at the scale divergence loop, if an LLM knows something, we do not consider that a learning. We think that LLM will just pick it up, right? If it does not, that is the thing that we learn, and we kind of put it in. Let me actually open up. This is what taste file ends up looking like. It's very much like a skill, but it is automatically learned. So after like building maybe 30, 40 CLIs with command code, these are all the things that it has picked up are my taste of building CLIs, right? And as the models have gotten smarter, this file has actually gotten shorter, right? So a lot of things that models now already know are, get automatically removed from here. So this is the taste file, right? And I built it for humans. I built it because I was like, the math was very simple, right? So here's a human developer, and they are gonna probably write a prompt, or maybe they are going to, edit a file, or say, no, this was bad, or say, yes, this was a, good tool call, right? And that is going to translate into software, right? So in this particular area, this thing, I felt like this was pretty important. In this piece, when a human is talking to an AI through their prompts, through their edits, through their saying something like, no, this is really bad, or saying something like, I always prefer using Commander, I always prefer using TypeScript, something like that. Maybe we should be learning something from this area and storing that as a taste file, right? So this became the taste.md file. The problem, however, with this approach is very quickly this year we saw in the same equation, humans are getting replaced by AI, right? AI is actually going even a step ahead, a step up, right? AI is being used to prompt, like in the human part is actually somewhere here now, right? This is the current world we live in, where a human tells in a coding agent that this is what I want, and the AI coding agent can spin up a bunch of different agents, do a bunch of different tool calls, do a bunch of different prompts, and do a bunch of different things, and write software, right? So I eventually ended up thinking that we can also learn the taste of an LLM, right? So consider this is an LLM. Since LLMs are writing more code than humans, we can probably learn the taste of LLMs, right? But it's not that useful. It's like, I cannot learn the taste of DeepSeek V4 Pro or Flash and share the taste with you, right? What would that taste really be helpful for you, right? And how would I actually go and learn that, right? So I ended up building this weird experiment of sorts where I picked an LLM, and that LLM, as you know, was DeepSeek V4 Pro. I also tried this on Flash, by the way. And I set a goal. I'm gonna burn 1 billion tokens across different programming languages. I did TypeScript, I did JavaScript, a lot of HTML in CSS projects, a bunch of Go, a bunch of Ruby, bunch of Python, and I think like probably 11 different languages that were done by Saqib, right? A bunch of different things, a bunch of different projects, and I ended up burning like 1 billion tokens. And out of this, I got this thing. I got the taste of DeepSeek V4 Pro and Flash. So I got a taste file, and this taste file is actually the taste of this LLM after 1 billion tokens on different projects. And I found so many amazing things in there. I found that, particular things like, when you're writing some particular Go routine, DeepSeek V4 trips up for some reason. If you're, writing some interface with TypeScript, if you just ask for that interface, it will just do it really, really well. But at scale, if you're doing it a lot, if you're sending like, thousands of different requests, if you're burning like 1 billion tokens at scale, this open model starts to struggle. And the taste file started building up a layer of different fixes that when you're doing this, do that. When you're doing this, you always stumble on doing this poorly, do that, right? This was an interesting experiment, as you can imagine, right? Alongside this experiment, I started thinking about how can I actually use this? Like if I have the taste of one LLM, where would I actually really need that, right? The second thing on the side that was happening was the errors, yay, and the pros and the cons that people were sharing in the community. Like, oh, DeepSeek is so good. Oh, wow, everybody's saying that it's so good, but I think it's a hype, and people are just claiming things that are fake. I tried it, tool calls are failing, right? And then I think within a couple of days or whatnot, we had probably crossed like 10 billion tokens consumed on command code. So I had enough data for errors of tool calls, like for this DeepSeek model, that I was able to figure out correlation between the taste that I had built in the tool call errors that were happening because of DeepSeek. And something became apparent. Like it was like, oh shoot, right? there's like a very clear pattern of things that this model is doing wrong. So I started with just 4 tool repairs. You know how there is a database migration, right? A database migration is like this. Maybe you are using Supabase or some, Postgres or something like this, right? So you generally have like this migration folder, right? And in this folder, you have probably, some date file with some, we change this table to fix username or whatnot, and .sql, right? And then you have like a bunch of files like this, you know, I don't know, table fix, authors or something, right? So this is how your migration folder generally looks like, right? So I started ended up building something very similar. I called it repairs, and I started looking at, you know, this is the repair tool harness part of our command code, right? So I started building something similar, right? And it was like, you know, I started taking a look at what are the most common you know, things that I see across different models. So not just DeepSeek, but GLM, Qwen, and a bunch of others. And I started to pick up on things. And these were the four most common tool call errors, right? And this is what my repair folder generally kind of looks like, right? So when you are sending null for an optional field, a lot of these open models just omit it. Think of it like this. Think of it like you have like a shell tool. Think of it like a function, right? It's a shell function, and shell function can accept, I don't know, it can accept like a, p, c, d, like four arguments, right? One argument actually with four properties, right? And maybe the C and D arguments are actually optional. So what I saw was that deepseek-flash would, instead of sending an empty value, it would just send null, and our, you know, repair our you know, Zod error schema was super strict. It would just reject it, right? And in other cases, it would be emitting something like this, which is not, which is a JSON array of sorts as a string, when the tool was actually, the tool schema was actually expecting an actual array, not a JSON string, right? And then in many cases, I saw that it started wrapping up arguments with a JavaScript object for no reason at all, right? As empty placeholder. So imagine you were expecting a value for D, but instead you got this weird thing, right? So it's not null. It's just an empty JavaScript object. So it will probably trip up this tool call a little bit, and whatever you know, error handler you are using, or the type you know, validator, what do you call it, library you are using, we use Zod, right? That Zod library would be like, oh no, you can't do this, you can't send this thing, this is against the schema we sent you, right? So this back and forth was happening, right? And it actually looked something like this. So think of this as command code, and this is your LLM, and this LLM right now is anything from DeepSeek, Qwen, GLM, Minimax. I think I didn't try on the Nemo models, but there was also Kimi, right? These were the models that I tried early on, right? So you're sending your LLM this data. You're saying, you know, you can have a shell tool call, and it expects A, B, C, and D. And this A, B, and C, and D could be like, I don't know, let's call it, you know, what is your shell command? It is expecting a command, and you can also tell it when to shut down, like, you know, the time when I think the idle time or something like this, right? That is quite common in shell tool calls. And the LLM in return is actually doing something very, very crazy, right? So here's your prompt. Prompt is, this is your the developer saying something like, you know, can you tell me something related to shell tool call, and the tool call is actually being transferred through your you know, coding agent to the LLM. In the LLM, instead of returning back a tool call that has some data, like, you know, I don't know, run cat command or something, right? Uh, um, what is happening? Run cat command or something, and your you know, tool harness, your coding agent is expecting some idle time here, like 9,000, like 9 seconds or something, right? And instead of this, it is sending this weird bug, right? Yeah, instead your LLM is returning something weird, which is not conformant of the schema of the tool call, right? So what happens here is, so this was your coding agent, right? So this was CMD, and this was your tool schema, and this is the tool call that we got from the LLM, right? And now that this tool call is a bad tool call, what's going to happen is Zod is going to take a look at it, and Zod is our type validator, and it's going to probably say, you can't do this. And it's going to probably return some giant big error object, which will probably be saying something like, you know, I received this empty thing, and I was expecting either you will send me nothing, like, I don't know, you will send me null, or you will send me a number value for this particular argument, right? And this error is now going back to an open model, right? So here's the problem, right? The open model will continue to send you back this thing. And it will do that for like 50 times. That was the thing that I actually discovered. Like, it will, on average, it was failing like 56 times. You would be getting the same bad tool call for 56 times. And Zod would be responding back with the error. Like, yeah, you can't do that. Fix your input, and then I will run this tool, right? So I was like, I don't know. Maybe I can figure out if there is a limited number of these bugs, and I can write a small repair harness on top of this, which would actually repair the tool call, and fix it and run it, and then also send back a note, a fixed note to the LLM. Think of it like you are teaching somebody how to drive a car, right? And you're sitting here, and the person who's learning how to drive a car is sitting here, and that person is about to hit a truck, right? You have two options. You can let them hit that truck and then teach a lesson of lifetime that, this is not how you should have done that. Or you can stop them, fix what they are doing wrong. Once you have saved them from that accident, you can explain that, you should have done this. Your speed should have been this. And while you were like, 3 meters before this giant truck, you should have pressed your brake, because trucks happen to have pressure brakes and they can stop anytime, right? So there are two options. You can either tell them, well, this is your error, go fix. And by that time, they are already dead, right? And probably you along with them. Or you can tell them, you can fix, repair what they are doing wrong. Once you have saved them from that accident, you can also then add a note like, this is what you should have done in the first place. So most of the harness right now in this space are doing just this. They get a bad tool call, they let it fail, and then they send back that error, but your session is already ruined. Your LLM, as a human, think of it like this. If you are interrupting a human from speaking 56 times in a row, when they are trying to help you build something, they will get pissed off. I always think of these LLMs like they have like a human, like because they're trained on our data, they act like humans, right? They will get pissed off. Their value to your task will decrease. Their intelligence, their cognitive ability, their capability will decrease, and the overall quality of output will also get decreased, right? So instead of doing this back and forth, if you can fix and repair that bug deterministically and send back a note, I fixed this, here's the tool result, you should have actually done this, that can have amazing results. So I tried that, right? So in this scenario, what I did was, I was like, okay, let's break it down. I will probably try to fix all of this. Okay, this is taking too long. Okay, instead of Zod sending back that error, I redirected this thing to a repair harness. So we now have a repair harness, right? So as soon as Zod figures out, oh, that this tool call was bad and we have a bug, the repair harness actually has something like a migration, something of like a migration. It looks like this. Okay, I have this thing, and I know how to fix it, right? And what we do is we're like, okay, we can deterministically fix this, and a repair runs, and I call that repair, let's call this, I don't actually remember what I call it, empty JS repair, JS object repair. So we have a bunch of repairs, and this fix will go back to our repair harness, and repair harness will match this with, okay, we can actually fix this, and we will send this as an input, and we'll get back this output. Since we were expecting the idle time, and since there was a bug here, we can make a deterministic, call here, and we can say, okay, the idle time could be something like, I don't know, 3000, right? And now this is what we have, and CMD will send back this as a tool result. But wait, just a minute, right? There's more interesting stuff that's going to happen here. So once you send this back, your whatever LLM you're using, open or close, it will now have a really good tool call result, and it will be able to continue doing what it was doing in the first place. A lot of people would have thought like, this is it, right? because I am me, I thought maybe I can learn how well this does in production. So I made this repair, made it live, watched it 3 hours later, almost 6 hours later. And in the night, I was able to figure out that this is just still failing. It is able to repair like just 1% of the bad tool calls. and we have 96%, maybe 98% of the tool calls that are repairable, but we are not able to repair them. And that was happening because right after this thing happens, let me actually make some more room for this. So right after this happens, open models do the same bad thing. They are going to send back the same bad command, right? So the next tool call you get, you are again going to get something. I don't know, maybe you are running something echo or whatnot. You're again going to get that bad thing, that error that was wrong in the first place, like this thing, right? And it would slow down. It would be just expensive. Sometimes it would do some weird thing that would cause it to just absolutely fail. And I thought to myself, what if, back to this example, what if I didn't just save this person from an accident, but also told them what they were doing wrong, right? Which is what we were trying to do here, right? Uh, I have a feeling that the way these open models are trained, they have this weird alpha male energy of sorts where they think whatever they are sending to you is right. Right? Maybe they are being distilled from big closed commercial models, and their training data set is something like whatever this commercial model is saying is correct. So just learn what they are saying. So the open model ends up being whatever I'm doing is correct, right? So if you pass back a Zod error, the open model again says, no, you are wrong. I'm not going to listen to your error. This is just wrong. What I'm sending you back is the correct thing. So what happens is, if alongside this tool result, if you add such a small node, like this is a repair fix node on our end, right? I call it repair node, right? And that repair node is explaining exactly what Zod was saying alongside the correct result, right? So here's the correct result. This is what you should have done in the first place. But here's the repair node. You should actually, from now on, do this. This becomes the entire tool call that is sent to, I don't know, DeepSeek or some LLM. In the very next tool call they send, they stop making those mistakes all of a sudden. So this is such a minimal thing, and it has such a big impact. You can't believe it, right? It started with, when an open model sends a bad tool call, you repair it deterministically without wasting any tokens, and you send back the correct result or near correct result by guessing what that model is doing. For example, if this was a readFile tool, they would send no data of offset. Like, are you trying to read 100 lines from the bottom or the top of this file? So I would just say, okay, since I don't know, I would repair it and send them just the first 100 lines, right? But if that was a log file and the repair note was there, the LLM would quickly understand, oh, no, I actually wanted to see what are the last 5 or 10 lines of this particular log file, and would very quickly repair itself, right? And think of it like this, you just made a mistake because you were thinking about something and you were talking about something else, and you just ended up saying something, and without breaking your flow, somebody says, you mean this? And you're like, yeah. And then you continue. That is what this is, right? The cognitive load that this particular open model has, when you have like your 1,000 messages deep and 2,000 tool calls in there, a long session, a small tool call break can cause the model output quality to completely drop. And because you just repaired it, it stays the course. Now it can run 12-hour long, super long sessions. It can really help you, right? And this is not this is obviously a model problem, and they can probably fix it in future models as well. But right now, no other coding agent harness is doing that. So I thought this was really good. And I didn't want this to be like, oh, we only do this. I was like, this should be open. We should all have a really good experience with tool calls, especially with open models. So I wrote about it. The failure is not random. It is a small, finite, compositional, set. It's only these things that I discovered that day, right? And the tool repair, harness is just, they're like 30 to 100 lines of code that can deterministically run a small compute code, and it can just fix it in place. Your tool results go back to the model with a repair node, right? And it just becomes really nice. Overall, this translated into a massive outcry. It's like a thing that people didn't expect, right? A lot of people tag DeepSeek. Oh, is it true? And a lot of people wrote like a bunch of different small harnesses. I saw like 10 different versions of this thing for Pi. I saw something for open code. I saw something for what is it called, Hermes agent, right? A bunch of people, because this is out there and open, and the entire process is right there, and I'm not like gate blocking it. I'm not saying you can only have this in command code. A lot of people were able to discover a lot of shape invariants and fix them, right? And it just started this new thing, which is like Once you have these repairs in place, and once you have a coding agent like command code that can self-repair, self-learn, and continuously learn, what you have is a consistent, amazing feedback loop that is consistently figuring out errors and invariants in across different open models in fixing them, right? In process, improving the speed, the flow, the quality of the output, and saving you a lot in token cost, right? So it started with just 4 tool calls, by the way. It started with 4. The next step was around 12 to 16 based on different LLMs. Like qwen have different quirks. DeepSeek is very different. GLM, for some reason, does not make a lot of mistakes. Kimi makes a lot less mistakes, though. Kimi K2.6 stays my top favorite open model so far, right? But once I fixed DeepSeek through these tool repairs, deepseek-flash is one of my favorite models. It is so good. It is better than Claude Haiku right now, cheaper than, like, maybe 10, 20 times cheaper than that. And if you know what you're doing, you can just ask it to do it and it will just do it, right? As far as it is not breaking up on weird tool call errors, right? And now they're like, I think 56,000 repair invariants we have. Like we have variations of 56,000 different small little tool call migrations based on the language, based on the model that you're using, based on the scenario. And we're continuously discovering more. And this number actually goes up and down. Like models tend to become better at different times. Like for example, the same error that I just discussed here, most of the times DeepSeek does not have this error, which is so odd. Like maybe I have a feeling that when the capacity of inference goes down, when there are a lot of people using DeepSeek, it tends to become less intelligent. It tends to make a lot more mistakes, and that is when these tool call issues start to show up. So at a trillion scale, we are at a trillion scale right now. We have a trillion, more than a trillion tokens per month in command code. We see this so many times. We see this hundreds of thousands of times, right? So by building these small little repairs, we are saving you both cost, speed, and we are fixing these open models. It's such a massive thing, right? It's such a benign thing, and it helps in so many different ways, right? So this ended up becoming a thing, as you can imagine, right? A lot of people ended up talking about it. Here's Paul, who created the impeccable design scale, and he was like, this is super interesting as an idea. And then there were like a bunch of different other people, right? And a bunch of people started trying out. All of a sudden, a lot of people started saying, I don't know about this. Maybe this is not as much. And I ended up like doing, this is when the tool repairs were like at 36K. I ended up actually creating a small info icon of sorts. Whenever you see this in command code, you would know that this thing, whatever tool call that was running with whatever open model was repaired 3 times with 3 different repair migrations before we sent back the result to the LLM. And you can see, okay, it's always like this was repaired once, it was repaired twice, it was repaired thrice. Obviously, as you can see, this is just a small smoke test where when the LLM was editing a file and we were expecting a file path, it sent us path, right? When we were expecting old value, it sent us old underscore string as the argument. So we just deterministically replaced this with that and fixed the tool call, and also the new string, new value, right? So these are the 3 tool repairs that happened before this tool could actually run, right? If you were not using command code, or if you were using a coding agent that does not have repairs in it, right, it would just have potentially failed here, right? And then it would have failed here and here, right? So it's saving you a lot, right? And that led to a bunch of different things. One of the things that led to was, command code got adopted a lot. We are now 2nd or 3rd biggest coding agent usage-wise on different leaderboards, like on Vercel, which is one of our AI providers. They have an AI gateway. We also host GPUs ourselves. And I ended up sharing a lot more around this thing. I ended up doing the same thing with Kimi. So if you are, wanna go down that road, you wanna see how Kimi K2.6 tool repairs work, you can go read this as well, and a bunch of different other things. Yeah, with that, if you have any comments, suggestions, feel free to share. With that, I'm out. Use your code for good.